I want to take a question that most physicists would not touch in a serious professional context and treat it with the full precision it deserves. The question is, what would actually happen if an extraterrestrial civilization made contact with Earth? Not in the science fiction sense, not in the sense of speculation about alien motivations or alien biology or what they might look like. In the physical sense, in the sense of what the laws of physics, the structure of interstellar space, and the specific constraints on information and matter transfer across cosmic distances actually imply about what contact would look like and what its consequences would be. Because the popular conception of alien contact, shaped by decades of science fiction films and novels, is almost entirely divorced from what the physics allows: the dramatic arrival of vast fleets of spacecraft, the ominous transmission from a nearby star system, the ambiguous signal from deep space that might be artificial. These scenarios map very poorly onto the specific physical realities of interstellar travel, interstellar communication, and the constraints of the speed of light. I want to go through each of the physically plausible forms of contact in order of their distance from the assumptions of the standard science fiction narrative and closest to what the physics actually supports, and describe what each one would actually mean, what we would observe, and what the implications would be for our understanding of the universe and our place in it. Let me start with the form of contact that is both the most likely and the most frequently dismissed in popular culture: the electromagnetic signal. Any civilization that has developed radio technology broadcasts electromagnetic radiation that propagates outward from its home star at the speed of light. We have been doing this since approximately 1895, when Marconi's first radio transmissions began, though the earliest leakage would have been very weak. The stronger and more distinctive broadcasts began in the 1930s and 1940s with the development of television and radar. Our radiosphere, the expanding bubble of electromagnetic radiation carrying recognizably artificial signals, now has a radius of approximately 80 to 129 light years, depending on how you define the detectability threshold. Any civilization within that radius that has a sufficiently sensitive radio receiver pointed at our solar system would know we are here. The inverse is also true. Any civilization that has been broadcasting for longer than we have, or that broadcasts with greater power, might be detectable by us. The SETI program has been searching for such signals systematically since 1960, when Frank Drake pointed the Greene Bank radio telescope at two nearby stars, Epsilon Eridani and Tau Ceti, as part of Project Ozma. In more than 60 years of searching, no confirmed extraterrestrial signal has been found. What would happen if one were found? The physical reality is profoundly anticlimactic compared to the science fiction version, and I want to be specific about exactly what it would look like. The detection would begin with an anomaly in data, a signal at a specific frequency with a specific pattern that a researcher or an algorithm noticed did not match the noise floor or any known astrophysical source. The signal might be a narrowband continuous wave, a single frequency much narrower than any natural astrophysical signal. It might be a repeating pattern with a mathematical structure. It might be something we have no framework to characterize. The first response would be internal checking. Is this an artifact of the instrument? A reflection from a satellite? A radio frequency interference source on the ground? Radio frequency interference from human technology is the bane of every radio telescope, and distinguishing a genuine extraterrestrial signal from terrestrial interference is the first and most difficult challenge. The WOW signal detected at the Ohio State University Big Ear Radio Telescope on the 15th of August 1977 is the strongest candidate for an artificial extraterrestrial signal ever detected, but it was never confirmed by any subsequent observation despite many attempts. Its source remains unknown. After internal verification, the team would contact other observatories for independent confirmation, A real signal should be detectable by any radio telescope pointed at the same location in the sky. If multiple independent instruments at multiple locations detect the same signal from the same celestial coordinates, the probability of terrestrial interference drops to near zero. The SETI protocols specify that before any public announcement, the discovering team should attempt independent verification, contact the IAA SETI Permanent Committee, and follow the Declaration of Principles Concerning Activities following the detection of extraterrestrial intelligence, first adopted in 1989 and subsequently updated. The protocol emphasizes that no response should be transmitted without broad international consultation. In practice, the secrecy requirement of the protocol would be extremely difficult to maintain. Modern observatories have large teams, preprint servers, and instant communication. A genuine extraterrestrial signal would likely be public knowledge within hours of a credible detection, regardless of any formal protocol. The history of science suggests that major results leak before official announcement. The distance to the source determines everything about what the signal means. If the signal comes from a civilization 100 light years away, what we are receiving is a snapshot of that civilization as it was 100 years ago. The civilization that sent the signal may have completely changed or ceased to exist. In the century it took the signal to reach us. Any response we send will take another 100 years to arrive. The total round-trip communication time is 200 years. If the signal comes from 1,000 light years away, the civilization we are detecting existed 1,000 years ago when the Crusades were beginning in Europe and the Song dynasty was at its height in China. Any response would arrive 2,000 years from our current date. This is not a dialogue in any meaningful human sense. It is the exchange of monologues across a chasm of time so large that the civilization on either end might be unrecognizable to its successors by the time a reply arrives. The content of the signal would be the subject of extraordinary scientific effort. The most likely structure for a decodable interstellar message would exploit mathematics and physics, which are arguably universal. A sequence of prime numbers, a mathematical constant like pi, or a pattern based on atomic transition frequencies would confirm artificial origin and suggest intelligence without requiring shared cultural context. The hydrogen line at 1,420 megahertz is the most commonly proposed frequency for deliberate interstellar communication because it is the emission frequency of the most abundant element in the universe and would be known to any civilization that has developed radio astronomy. A more complex signal might use a self-describing encoding, a message that explains its own structure before conveying content. This is the approach used in the Arecibo message of 1974, which was a binary encoded image that described its own format if laid out correctly. More sophisticated encoding schemes have been proposed by Carl Sagan, Hans Freudenthal, and others. The fundamental challenge is that there is no universal language, but there are universal mathematical and physical facts that any intelligent species must have discovered, and these can serve as a foundation for building more complex communication. Now let me move to the scenario that is orders of magnitude less likely, but orders of magnitude more dramatic. The arrival of a physical object from another star system. We have already received one. In 2017, the object designated 1I, 2017 U1, subsequently named Oumuamua, passed through our solar system on a hyperbolic trajectory, coming from the direction of the constellation Lyra and departing toward Pegasus. Its velocity, 26 kilometers per second relative to the Sun, was higher than the escape velocity from the solar system, confirming it was an interstellar object rather than a solar system body. It is the first confirmed interstellar visitor to our solar system. Oumuamua was strange. It was elongated, possibly cigar-shaped or pancake-shaped, with an aspect ratio unlike anything seen in solar system objects. It was red, suggesting a thick organic or mineral coating from cosmic ray processing during its interstellar journey, and it exhibited a non-gravitational acceleration, a deviation from the trajectory expected for a purely gravitational orbit that could not be explained by outgassing of volatiles, the usual cause of such deviations in comets. No coma of gas or dust was detected around Oumuamua. Avi Loeb, the chair of the Harvard Astronomy Department, suggested in a 2018 paper that the non-gravitational acceleration could be explained if Oumuamua were a light sail, a thin sheet of material being pushed by radiation pressure from the Sunday. This required it to be extremely thin, perhaps millimeters in thickness, and of artificial construction. Most of the astronomy community was skeptical and proposed alternative explanations, including that it was a hydrogen iceberg, a chunk of molecular hydrogen ice that would have sublimated invisibly under solar heating, producing the acceleration without a visible coma. This and other natural explanations remain contested. Oumuamua demonstrated something important regardless of its origin. Interstellar objects do enter our solar system. The interstellar medium is not empty. Objects ejected from other planetary systems during formation or evolution traverse the galaxy for millions or billions of years. Some of them pass through our solar system. If any interstellar civilization has been launching probes or ships for millions of years, some of those objects might be in or have passed through our solar system. This raises a specific and interesting possibility. What if an alien probe has already passed through our solar system or is currently passing through it and we failed to recognize it? Oumuamua was detected only during its departure from the inner solar system, too late for any close observation. Smaller objects at greater distances would have been completely undetectable with any current survey telescope. The Vera Rubin Observatory, which began full scientific operations in 2025, will survey the sky with a sensitivity and cadence that will detect interstellar objects at much earlier stages of their trajectories, giving months or years of observation time rather than days. If interstellar objects the size of Oumuamua or larger pass through the inner solar system at the expected rate, Rubin will find several per decade. Whether any of them will show the anomalous properties of Oumuamua, suggesting artificial origin, is unknown. We have already received one. In 2017, the object designated 1I, 2017, U1, subsequently named Oumuamua, from the Hawaiian phrase roughly meaning first messenger from afar, passed through our solar system on a hyperbolic trajectory, coming from the direction of the constellation Lyra and departing toward Pegasus. Its velocity relative to the Sun at entry, 26 kilometers per second, was higher than the escape velocity from the solar system, confirming it was an interstellar object rather than a solar system body. Oumuamua was strange in multiple specific ways that are worth enumerating carefully, because the strangeness is in the details, and popular accounts often get the details wrong. Its shape, from the way its brightness varied as it tumbled, astronomers inferred that it had an extreme aspect ratio, either very elongated like a cigar or very flat like a pancake. Estimates range from 6 to 1 to 10 to 1 for the elongated model, or from 5 to 1 to 10 to 1 for the flat model. Neither morphology has been seen in any solar system object, where comets and asteroids typically have aspect ratios below 3 to 1. The flat model is less intuitive, but actually better supported by the light curve, its surface. The color of Oumuamua was notably red, more red than typical cometary nuclei. This is consistent with the organic-rich mantles that form on small bodies exposed to cosmic ray bombardment over long timescales. The reddening suggests it had been in interstellar space for at least hundreds of millions of years before entering our solar system. Its trajectory. As Oumuamua receded from the Sun, its path deviated from the gravitational trajectory expected for a purely ballistic object. The deviation was small but highly significant statistically, requiring an additional acceleration of approximately 10 to the minus 4 centimeters per second squared at a heliocentric distance of 1.4 astronomical units. For comparison, the expected radiation pressure on a typical rocky or icy body of Oumuamua's estimated size would produce an acceleration roughly 100 times smaller. To explain the observed acceleration by radiation pressure would require Oumuamua to have an extraordinarily high area to mass ratio consistent with a thin flat disk or sheet with a mass per unit area of approximately 0. 1 grams per square centimeter. Its lack of a coma. Comets in the inner solar system almost universally develop a coma, a cloud of gas and dust as solar heating sublimates volatile ices. Oumuamua showed no coma in extensive observational campaigns. This is unusual for an object experiencing the sun's heat for the first time from interstellar space, where it would have been very cold for millions of years. A comet-like body of its size should have shown outgassing. It did not. The combination of these properties, the extreme shape, the non-gravitational acceleration without a detected coma, prompted Shmuel Bialy and Avi Loeb to submit a paper to the Astrophysical Journal Letters in 2018 arguing that the data were consistent with Oumuamua being a light sail of the right dimensions would produce the observed radiation pressure acceleration without any outgassing and would have the flat morphology implied by the light curve. The paper explicitly acknowledged that this was a speculative hypothesis, but argued it was consistent with the data. The mainstream response proposed natural alternatives. The hydrogen iceberg hypothesis suggested that Oumuamua was made of molecular hydrogen ice, which would sublimate invisibly under solar heating, providing the non-gravitational acceleration without a detectable coma. This was subsequently challenged on theoretical grounds. Molecular hydrogen ice is not expected to survive the interstellar radiation field over the time required to reach our solar system from its hypothetical origin. Other proposals included nitrogen ice, fragments of exopluto objects, and various fractal dust structures. Each has specific difficulties. The honest assessment is that Oumuamua remains unexplained. No natural explanation has been accepted by the full community. The artificial explanation has not been confirmed by any independent evidence. The object passed through the inner solar system, and we had only a few weeks to observe it before it receded beyond detectability. We will never have more data from Oumuamua. What Oumuamua demonstrated, regardless of its origin, is that interstellar objects do enter our solar system. The Vera Rubin Observatory, which began operations in 2025, surveys the sky with sufficient sensitivity to detect interstellar objects at much earlier stages of their trajectories. If Oumuamua-sized objects transit our solar system at the rates suggested by its detection, Vera Rubin should find several per decade. If any of them show the anomalous properties of Oumuamua, we will have months or years of observing time to characterize them properly. Now let me address the scenario that everyone pictures, but that the physics makes extraordinarily constrained: the arrival of a spacecraft from another civilization. I described in the previous video about getting home from Mars, and in the earlier video about Proxima Centauri b, the fundamental physical constraints on interstellar travel, the energy requirements, the radiation environment, the time required. These constraints apply to any civilization, not just ours. Any civilization anywhere in the universe must obey the same laws of physics. They cannot exceed the speed of light. They cannot circumvent the rocket equation without an external energy source. They face the same radiation environment in interplanetary and interstellar space? What does this mean for a civilization capable of reaching Earth from another star? A spacecraft traveling at 10% of the speed of light, a very optimistic but physically plausible speed achievable with advanced nuclear propulsion, would take approximately 42 years to reach Earth from the nearest star, Proxima Centauri, and thousands of years to reach Earth from typical stars in the galaxy. At 0.01% of the speed of light, which is more representative of what advanced chemical or early nuclear propulsion could achieve, the journey from the nearest star takes 40,000 years. For any civilization to make this journey, they must have motivations that sustain a program of interstellar travel for decades to thousands of years, the technological capability to sustain a spacecraft over that duration, and the specific knowledge that Earth exists and is worth visiting. The last of these is itself constrained by the speed of light. They can only know Earth exists if light from Earth has already reached them. For them to know we are here, their star must be within the distance our electromagnetic signals have already reached, approximately 129 light years. A civilization at 100 light years would have learned of our radio emissions roughly 30 years ago in our frame. If they immediately launched a spacecraft at 10% of the speed of light, it would arrive in approximately 1,000 years. Their spacecraft would be ancient technology by then. We would have 1,000 years of warning. The fastest conceivable spacecraft at near light velocities requiring energy comparable to the total output of the civilization star would arrive in approximately 100 years. These timescales are not dramatic from a human perspective. They are long. The panic of a sudden arrival from space with no warning and no time to prepare is physically impossible given the speed of light. If a civilization capable of interstellar travel is coming here, the light from their civilization reached us before their spacecraft did. The signal, if we detected it, would give us decades to centuries of warning. What if a civilization is already here, having arrived before we developed electromagnetic communications? This is the premise of many science fiction narratives. The physics does not rule it out, but makes it very unlikely for specific and interesting reasons. Any spacefaring civilization from beyond our solar system would have needed to travel for a very long time to reach us. During that journey, they would have had every opportunity to study the inner solar system from afar, using telescopes of the quality they must possess to be a spacefaring civilization. They would have known about Earth's biosphere, its atmospheric composition, its surface features, long before arrival. If they arrived millions of years ago, they arrived before complex animal life, before the emergence of intelligence. If they arrived thousands of years ago, before recorded human history, and are still here, they have been remarkably quiet for a remarkably long time. The absence of any unambiguous evidence for alien presence on Earth, despite thousands of years of human record keeping and increasingly sensitive scientific monitoring of the planet and its near environment, is itself a significant constraint. It does not prove that no such presence exists, but it shifts the probability toward explanations that do not require ongoing concealment of a civilization capable of interstellar travel. Let me now turn to what I think is the most interesting physical question about alien contact. What would their technology tell us about the laws of physics? If a civilization can travel to Earth from another star at speeds significantly higher than our best current technology, they must have solved physics problems that we have not yet solved. Specifically, if they travel faster than any chemical or nuclear rocket can go, they must have access to energy sources or propulsion mechanisms beyond our current understanding. This is not a statement about what is physically possible. It is a statement about the gap between their knowledge of physics and ours. The laws of physics that we know do not permit faster than light travel. If they are traveling faster than light, They know physics we do not. They have discovered aspects of the physical world that our current models do not capture. For a physicist, this is the most exciting implication of genuine contact with a spacefaring civilization. Not the biological, cultural, or political implications, though those are enormous. The physics, whatever technology they use to cross interstellar distances, would be a window into the physics we are missing. The specific possibilities include a method for generating and sustaining antimatter at scale, which would allow much higher specific impulse rockets than any we can build. A way to extract energy from the quantum vacuum, the zero-point energy that fills all of space, according to quantum field theory, a method for manipulating space-time geometry to create shortcuts or wormholes. If general relativity admits such solutions in the presence of exotic matter, or a propulsion mechanism we have not yet imagined, based on physics we have not yet discovered. Each of these possibilities connects to specific open questions in fundamental physics. The quantum vacuum energy is real and has been measured in the Casimir effect and in the cosmological constant. Whether it can be extracted for propulsion is unknown, and there are serious theoretical arguments against it, but it is not obviously forbidden. Exotic matter with negative energy density required for traversable wormholes is forbidden for all known forms of matter, but might exist in some quantum gravity contexts. The possibility space for physics beyond the current standard model is genuinely large, and a civilization with a billion-year head start on physics research would have explored much of it. The deepest implication of contact with a technologically superior civilization is not military or political, it is epistemological. If they have solved problems we have not, if they know physics we do not, then our current understanding of the laws of nature is incomplete in ways that have practical implications. The gap between Newtonian physics and quantum mechanics, which took humanity 2 centuries to discover, completely transformed technology in ways that Newton could not have anticipated. The gap between our current physics and whatever physics underlies interstellar travel would be comparable or larger. The technology consequences would be beyond our ability to predict. Let me now turn to what I think is the most interesting physical question about alien contact. What would their technology tell us about the laws of physics? If a civilization can travel to Earth from another star at speeds significantly higher than our best current technology, they must have solved physics problems that we have not yet solved. Let me be specific about what those problems are, because they are among the deepest open questions in fundamental physics. The first is energy density. Chemical rockets achieve specific impulses of approximately 450 seconds, limited by the energy stored in chemical bonds. Nuclear thermal rockets can reach approximately 900 seconds, limited by the temperature that rocket materials can withstand. Nuclear pulse propulsion could potentially reach thousands of seconds. Ion drives achieve specific impulses of 3,000 to 10,000 seconds, but with extremely low thrust. The energy per unit mass of antimatter, the most energy-dense fuel allowed by known physics, is approximately 90 petajoules per kilogram, orders of magnitude beyond any chemical fuel. A civilization using antimatter propulsion could potentially achieve transit times to nearby stars on human timescales. The production of antimatter at scale is the key limitation. We currently produce approximately 15 nanograms of antihydrogen per year at CERN, at an energy cost orders of magnitude above the energy the antimatter contains. Scaling antimatter production to the level needed for interstellar propulsion would require advances in energy production and particle physics that we cannot currently envision. But there is no physical law that forbids it. It is an engineering and energy problem, not a fundamental physics barrier. The second open problem is whether space-time can be engineered. In 1994, Miguel Alcubierre published a paper showing that general relativity's equations have solutions describing a space-time geometry that would effectively allow faster-than-light travel by contracting space in front of a spacecraft and expanding it behind, carrying the spacecraft along without the spacecraft itself moving faster than light locally. The Alcubierre metric is a mathematical solution to Einstein's equations, but it requires exotic matter with negative energy density to maintain the warp bubble. Negative energy density is not forbidden by quantum mechanics. The Casimir effect demonstrates that the quantum vacuum between two closely spaced conducting plates has a lower energy than the vacuum outside, a form of negative energy density. Whether the negative energy that can be generated by quantum effects is of the right form and quantity to maintain an Alcubierre bubble is an active area of theoretical research, and the answer appears to be that the required amount of negative energy is far beyond anything achievable with known physics. But if a civilization has solved the problem of negative energy at scale, they have solved a problem that sits at the intersection of quantum field theory and general relativity, one of the most fundamental open problems in theoretical physics. The third open problem is whether wormholes, shortcuts through space-time, are physically realizable. General relativity admits wormhole solutions, first studied by Einstein and Rosen in 1935 as the Einstein-Rosen bridge, and later by Kip Thorne and Morris as traversable wormholes. Like the Alcubierre metric, traversable wormholes require exotic matter with negative energy density. The ER equals EPR conjecture, developed by Maldacena and Susskind, suggests that wormholes and quantum entanglement are the same physical phenomenon described in different languages, which would connect the problem of wormhole traversability to the deep structure of quantum gravity. I described the ER equals EPR conjecture in the video about black hole information. The connection between wormholes and entanglement suggests that the solution to the traversable wormhole problem, if there is one, lies in quantum gravity, specifically in the way entanglement creates the geometry of space-time. A civilization that has solved quantum gravity would potentially understand whether traversable wormholes are possible and, if so, how to create them. The specific implications of each of these possibilities for what alien technology would look like are quite different. Antimatter propulsion would produce characteristic gamma ray emission at 511 keV. The annihilation line from electron-positron pairs that might be detectable from approaching or departing spacecraft. Alcubierre drive spacecraft would produce exotic space-time distortions that, in principle, could be detected gravitationally. Wormhole technology would require the creation and maintenance of exotic matter configurations that might have specific signatures. For a physicist, the most exciting implication of genuine contact with a spacefaring civilization is not the biological or political implications, it is the physics. Whatever they use to cross interstellar distances would be a window into the physics we are missing. If they have solved quantum gravity, if they have created traversable wormholes or functional warp drives, we would learn more about the deep structure of space-time in the first year of contact than in all of human scientific history. Now let me address the question that this entire discussion points toward. Is there anyone out there? And if so, why have we not heard from them? In the context of this discussion about what contact would actually look like, the paradox has a more specific form, given that electromagnetic signals propagate at the speed of light and that any civilization that has developed radio technology has been broadcasting into space. Why has no signal been confirmed despite 60 years of systematic search? There are several physically distinct categories of answer. The first is that life and intelligence are genuinely rare. The emergence of life, the development of multicellular organisms, the evolution of intelligence, the development of technology. Each of these steps might be so improbable that we are among the first civilizations to arise in our galaxy, or possibly the only one. This is the rare Earth hypothesis, and it receives support from the astrobiology research showing how many specific factors contributed to Earth's habitability, as I described in the Proxima Centauri b video. The second is that civilizations are short-lived. Technology arises, and then civilizations destroy themselves before developing the radio technology they need to communicate, or develop radio technology and then destroy themselves quickly thereafter. The timescale for self-destruction, whether by nuclear war, biological catastrophe, ecological collapse, or other means, might be short compared to the timescale for contact. If civilizations typically last a few hundred years after developing radio technology before destroying themselves, the probability of two overlapping in time is small. The third is that communicating civilizations are rare because surviving civilizations stop communicating. Radio technology may be a brief phase in the development of any civilization. We ourselves are moving from broadcast radio to cable and fiber optic communications, leaking less electromagnetic radiation into space than we did in the mid-20th century. A civilization that transitions entirely to tightly directed or quantum encrypted communications might be effectively invisible from space even if it is still thriving. The fourth is that they are there, but we have not looked long enough or hard enough. 60 years of SETI is a tiny fraction of the galaxy's history. The search has been limited to specific frequency ranges, specific types of signals, and a small fraction of the sky at any given time. The parameter space for interstellar signals is enormous, and we have explored a tiny fraction of it. Each of these possibilities has different physical implications for what contact would look like. If civilizations are rare, the nearest is likely to be very far away, and any signal would be ancient and one-directional. If civilizations are short-lived, the window for contact is narrow and easily missed. If civilizations go quiet, they may be present in the galaxy but undetectable with current methods. The most honest answer to the Fermi paradox is that we do not know. The absence of detected signals is consistent with all of these explanations and many others. The universe has been around for 13.8 billion years. We have been looking for 60 years with limited technology and limited resources. The statistical significance of the null result is much smaller than it appears. There is one more concept that deserves attention before I close, which is the great filter. The idea was introduced by Robin Hanson in 1998 as a way to explain the Fermi paradox. The great filter is the name for whatever process or barrier accounts for the fact that we see no evidence of other civilizations. There must be some step in the development from sterile matter to galaxy colonizing civilization that is extremely improbable, a filter that almost nothing passes through. The crucial and unsettling question is where in the sequence the great filter lies. If the filter is behind us, it was some step in our past that was astronomically improbable. Candidates include the origin of life itself, the development of the eukaryotic cell, the development of multicellular life, the emergence of intelligence, or the development of technology. If one of these steps is the filter, then almost no other planet has passed through it, and we are likely alone or nearly alone in the galaxy. This is the comforting interpretation. We are special and unique, and the absence of others reflects how unlikely our existence is. If the filter is ahead of us, it is a barrier that almost all technological civilizations fail to pass. Candidates include nuclear self-destruction, engineered pandemic, ecological collapse, uncontrolled artificial intelligence, or some form of catastrophe we cannot yet imagine. If this is the case, then civilizations arise frequently throughout the galaxy, but almost never survive long enough to establish an interstellar presence. The Great Silence reflects not the rarity of intelligence, but the rarity of longevity. And we are approaching the filter The discovery of life beyond Earth, even microbial life, would dramatically change our assessment of where the filter lies. If we find microbial life on Mars or in the subsurface of Europa or Enceladus, it tells us that abiogenesis, the origin of life, is not extremely rare. The filter is not there. The filter must be further along the path in the development of intelligence or technology or their survival. If simple life is common, complex life is rare, and technological civilization is rarer still, the filter might be the development of intelligence. If life and intelligence are both common, and yet we see no civilizations, the filter must be ahead of us. This is the specific and unsettling implication of the Fermi paradox's great filter interpretation for the question of alien contact. The absence of contact is consistent with our safety and our uniqueness. But if we find evidence that life is common in the galaxy, that evidence is not only beautiful and affirming, it moves the filter forward in time toward us and makes the reason for the great silence more ominous. Let me close with what I think is the most important thing to understand about the possibility of alien contact, which is how it changes the picture of the universe we have developed in this series of videos. Throughout these videos, I have described a universe that is extraordinarily large, extraordinarily old, and extraordinarily indifferent to human concerns. The universe does not know we are here. The physics that governs the expansion of space, the formation of galaxies, the life cycles of stars, the structure of space-time, none of it cares about the specific configuration of matter that is a human civilization. And yet, the universe is also extraordinarily productive of complexity. It has produced, in the 13.8 billion years since the Big Bang, the conditions for chemistry, for biology, for intelligence, for science. The laws of physics that allow the universe to be so large and so old are the same laws that allow it to produce the kinds of complex, self-organizing systems that can look back at the universe and ask what it is. If intelligent life exists elsewhere in the galaxy, which is physically possible and by some estimates likely, then the universe has produced the capacity for self-reflection not once but many times, in many places, separated by distances that may make contact impractical or impossible. The universe contains observers without those observers being able to observe each other. The detection of an extraterrestrial signal or the arrival of an extraterrestrial object that could not be of natural origin would not just be a discovery about aliens, it would be a discovery about the universe. It would tell us that the emergence of intelligence is not an accident unique to Earth, but a property of the laws of physics themselves, a tendency of matter organized in the right way to become self-aware. That would be the most important discovery in the history of science. And the absence of contact, the great silence, is also a statement about the universe, though a more ambiguous one. It is consistent with our being alone, or nearly alone. It is consistent with civilizations dying before they can communicate. It is consistent with the universe being more generous with the emergence of intelligence than we know from our single sample. The silence does not tell us which of these is true. It is the most interesting, open question in the physics of the cosmos. If this changed how you think about the possibility of extraterrestrial life, and what contact would actually look like, tell me in the comments. Tell me whether you find the electromagnetic signal scenario or the physical artifact scenario more compelling and why. Tell me whether the specific physical constraints on interstellar travel make you more or less optimistic that contact of any kind is possible within the foreseeable future. And subscribe if you want to keep going into the places where the physics of the universe meets the most ancient and most important question that any thinking creature has ever asked.